Hey everyone, and welcome. If you're a junior engineer and you're maybe staring at your first big cooling load calculation, well, you are in exactly the right place. Today, we're going to break down one of the most important jobs in HVAC design. We're going to do a real, practical, step-by-step walkthrough using HAP software. Let's get into it.
It really all boils down to this one question. You get a set of drawings, just a simple floor plan, and somehow you have to figure out exactly how much cooling that building is going to need. It can seem like a huge puzzle, right? But it's actually a super logical process of turning pictures into data, and we're going to walk through it together.
So, the tool we're going to use for this magic trick is Carrier's Hourly Analysis Program, or HAP, as you're going to hear pretty much everyone call it. And there's a good reason. It's an industry standard. It gives us this really clear, structured workflow that basically just guides us right to the answers we need.
Now check this out. The way HAP organizes everything is just so smart. This project navigator you see on the left, that's our roadmap for the whole project. We start at the very top with the big picture stuff, like weather. Then we work our way down, defining the building, the individual spaces inside, and finally the systems that are going to cool it. It's a perfect path, from the outside in.
Okay, first things first. Every building has to exist somewhere, right? So before we can even think about calculating the cooling load inside the building, we have to tell the software what it's up against on the outside. This is our climate foundation.
So for this project, you can see we're working with a building in Cairo, Egypt. And what's great is that HAP comes preloaded with all the ASHRAE climate data from all over the world. We just pick Cairo, and bam, the software fills in the critical numbers for us. Now, I want you to focus on two values here. The summer design dry bulb, or DB, is 100.7 degrees Fahrenheit. That's our peak heat. And the coincident wet bulb, or WB, is 70.2. That tells us all about the humidity in the air. Seriously, these two numbers are the absolute bedrock of this entire calculation.
So here's the bottom line. Each of these little inputs tells a part of the story. The location, that sets the sun's path and angle. The climate zone, hot, dry, gives us a heads up on the challenges. The dry bulb temperature is the big enemy. It's the peak heat we have to fight. And the wet bulb tells us how sticky and humid that hot air is, which has a huge impact on our cooling load.
All right, we've got our climate locked in. Let's move on to the next step, which is honestly where it starts to get really cool. We're going to build a digital version of the actual building. It's time to make this architecture come to life inside the computer.
And this slide just shows the process perfectly. You import the 2D floor plan, and you basically just trace the outline of each room. And as you're doing that, HAP is in the background automatically building a 3D model. It's figuring out all the exact surface areas and volumes it needs to calculate how heat moves through the walls and roof.
But of course, a building isn't just a solid box, right? We have to go in and carefully place every single window and door. Why? Because windows are basically giant doorways for heat from the sun. Getting their size, their placement, and their properties defined correctly is absolutely critical for an accurate calculation. So what's actually happening inside these rooms we just drew? That's where something called space types comes in. The best way to think about them is as templates or like pre-made recipes. We tell HAP how a space is going to be used. Is it an office, a cafeteria, a meeting room? And it automatically applies all the right ASHRAE standards for lighting, equipment, and most importantly, how much fresh air we need for ventilation. And here's where we put those templates to work. We literally go through our model room by room. There's the cafeteria, the office, the HR department, and we assign the right space type to each one. This is what tells HVAC, hey, expect this many people in this room, and you're going to need to provide this much fresh air to keep them comfortable.
Okay, so we've defined the building, and we've defined what's happening inside it. Now, we've got to put on our HVAC designer hat. How do we group all these different rooms together for smart, efficient temperature control? Well, the answer is something called zoning.
This color-coded map just makes it so easy to understand. A zone is just a group of rooms that are all controlled by a single thermostat. We try to be smart about it and group rooms that have similar needs, like maybe all the offices on the sunny south side of the building become one zone. Because if you get this wrong, trust me, you'll have one person freezing while their coworker is sweating just down the hall. Good zoning is everything.
So, once our zones are defined, we can actually assign the equipment that's going to cool them. For this project, we're using a simple fan coil unit, or FCU, for each of our 6 zones. Just think of it as the local machine that's going to deliver the nice, cool air. This is pretty much our last big input step before we get to the good stuff.
So let's recap. We've fed the machine all the data. The weather outside, the building's shape, how it's being used, how it's zoned, and what systems are serving it. Now, it is time for the moment of truth. Let's see what all that hard work gets us.
This right here, this is the payoff. After all that careful clicking and data entry, one final click gives us the numbers that are going to drive the rest of the entire design.
And there they are. This table tells us pretty much everything we need to know. Let's just pick one, Zone 4. It needs a cooling load of 104.1 MBH. That's how much cooling power we need. And to deliver that cooling, we need an airflow of 2,563 CFM. That's how much air we have to move. Every single zone gets its own unique set of numbers.
And I can't stress this enough. These are not just numbers on a page. The entire design literally hinges on this output. That cooling load number, that tells us exactly how big our air conditioner needs to be. That CFM value, that tells us how big our fans and all of our ductwork need to be. Getting this right is the absolute foundation of a successful project.
So, there we have it. We have our loads, we've answered that first huge question, and turned a simple floor plan into hard engineering data. Now, the journey's not over, of course. The next big step is to take these numbers and start designing the physical system, selecting the actual equipment, sizing the ducts, and bringing it all to life. I really hope this walkthrough helped make the process a little bit clearer. Thanks for watching.